Good morning, fellow colleagues. My topic is devoted to the problem of anomalous ion transport and high current vacuum discharge. Let's speak about what is anomalous ion transport. This phenomenon is presented by a cathode plasma is directed movement towards to the anode, and anomalously means that the metal ions have energies much greater with the thermal ones. And various experimental papers point out that the near cathode plasma expansion rates are much higher than the thermal ones, as well as to the fact that the anomalous transfer of ions from the cathode to anode occurs, and particularly in a vacuum discharge. Here you can see experimental papers, and this overthermal motion corresponds to the kinetic energy at the level of tens of even hundreds electron volts. In vacuum arcs, the ion fluxes with such energies are actually observed, and the physical mechanisms are reliably measured. Since the kinetic energies of ions, that's more than 100 electron volts, can manifold exceed a vacuum discharge combustion voltages, for example 80 volts, they are commonly called as ions with enormously high energies. We try to explain it, to clarify this phenomenon, and we built a simplified kinetic model. Here you can see main simplifications of the model. We don't use particle in cell method and hydrodynamic approach. We described plasma using the classical distribution functions for individual plasma components such as electrons and ions. We considered only one type of metal thinly charged species, for example copper, and we consider only one spatial variable, one component of momentum and time, of course. We don't need to include any relativistic effects, and we don't include any external magnetic fields. Now you can see the main equations, such as collisionless Boltzmann or Vlasov equations for electrons and for ions. To couple the two equations, we use Poisson's equations, where the number densities of species are calculated using the distribution function, and exact solutions in quadratures you see here as boundary conditions for potential, which means the cathode is grounded and anode is connected to the ideal voltage supply. Now how do we calculate the total current? We based on the current conservation law, where the current densities are calculated such way, and the total current density you can obtain for these equations by the integrating over all coordinates. You can obtain this equation, and now you can see the anode voltage. You see the rise time about 100 picosecond, and the next time is constant. Now about method. As initial conditions, we took quasi-neutral cathode plasma inflow. This inflow is ensured by the continuous electrons and ions emission with different temperature. You can see the temperature for ions 1 electron volts, for ions 3 electron volts. Now we use Maxwell velocities distributions. This formula is here. We write the code in MATLAB using the GPU high performance computational features. Use such high precision numerical shape, more detail in this paper, and we use new uniform mesh 1000 by 3000 elements for electrons and ions, of course. Now let's turn to the results. You can see electron distribution function in approximately 1 nanosecond. Now you can see that the electron distribution, that the plasma insufficiently differs for the distributions in vacuum diode in case of predominant electron emission. These distributions are determined by the rapid motion of electrons and then the relaxation of current. After the current relaxation, current established near the child current values, and this result observed also in this paper. Now let's look to the ions. What happened to this? Now you see initial distributions, and then about 1 nanosecond ion distribution functions in logarithmic scale, and black curve is electrostatic potential, blue is electron density, and the red dashed is the ion density. Now you can see the so-called virtual cathode, classical virtual cathode in the case of predominant electron emission. At this time, about 1 nanosecond, ions does not has no influence, such great influence on the plasma inside electron plasma, but after that it's time about 10 nanosecond. You can see the ions because of continuous electron and ion emission. You can see that ions have gain energies much greater than the initial ion temperature, which, if you remember, 3 electron volts. And now you can see the distortion in vacuum cathode. You can see the initial voltage drop about 30 volts, and now towards the node you can see a relatively low electric field, but this region with electric field accelerates ions, and ions gain more and more energy. And in the region of approximately constant voltage, there are quasi-neutral plasma, but a little in the front of virtual cathode you can see region of electric field. In this, ions accelerate more and more towards the anode, and they gain energy. You can see about 300 electron volts. This is this mechanism is determined by the anomalously ions energy. And now about 100 nanosecond, you can see the ions decrease LLO energy because of in model we include resistance, and the voltage at the anode decreases, and the electric field in virtual cathode is also decreases as the vacuum virtual cathode approaches the anode. And now about the current. Now you can see blue line is the anode electron current density, and white is full current density calculated use this formula. You can see the current oscillations about 1 nanosecond, and establish new child current values. And at full current density you can see the non-trivial time dependencies, because this part about to 100 picosecond great influence has this term. And then after the anode voltage is set to the constant, this term is disappears. And after the virtual cathode approaches the anode, current densities is increases too, and increases because direct gap electrical conductivity increases too because of anomalous ion transport, and increases because of quasi-neutral plasma increases, number densities increases too. And now about conclusions. On the basis of physical kinetic description of the ions and electrons, ensembles of a particle's behavior in a self-consistent electric field. The initial stages of non-stationary electron beam formation process have been simulated for a vacuum diode with a cathode plasma emitter. We unambiguously showed for the first time that the cathode plasma velocities towards the anode is determined by a self-consistent electric field. Dynamics accelerating ions to the energies of tens or even hundreds electron volts. And now by the fact that the initial distributions of ions have non-zero distributions. The above-mentioned ion energies are observed in experimentals with vacuum arcs in a large number of experimental papers, such this paper. And most important, I think, that given theoretical explanations was obtained without introducing any artificial approaches, such as so-called electron beam deceleration. The approach considered always this requires any artificial interactions between charged particles, and they have a number of arbitrary speculative parameters. Now, that's all. Thank you for your attention.